Welcome. Welcome to the deep dive. In our, well, increasingly digital world, almost every single thing we do online, every action, it leaves some kind of trace.
Uh-huh. Like digital footprints.
Exactly. Every click, every system process starting up, every network connection, pinging back and forth, it all generates these things we call logs.
Right. And they're not just, dry technical files. They're more like, well, digital breadcrumbs. They tell the story moment by moment of what your systems are actually doing.
How they're performing, if they're healthy, or sometimes where things are starting to go wrong.
Yeah, and if you've ever managed a server or maybe built a complex app or even just tried to figure out why your home Wi-Fi is suddenly crawling,
Oh yeah, been there.
you run smack into the sheer volume of these logs. It can be, well, honestly
We're
overwhelming.
talking thousands, millions.
Could be. Potentially millions of messages, yeah, streaming in at the same time from all sorts of different places. And the huge challenge isn't just finding disk space for it all.
No, it's more than storage.
Way more. It's how do you efficiently collect all that, parse it so it actually makes sense, store it intelligently, and then crucially, understand it. How do you get real insight out of that flood?
It really is like trying to drink from a fire hose, isn't
Now,
it?
totally. Except the fire hose is spraying super compressed, vital information right at your face.
Huh. Okay, that's a perfect picture. So how do you process that fire hose without, drowning?
Well, that's where today's deep dive comes in. We're going to unpack this really fascinating and I think incredibly useful open source project. It's called aiosyslogd.
That's aiosyslogd.
Right. And at its heart, it's a high performance asynchronous syslog server. It's built specifically to tackle this exact problem.
So think of it like an intelligent filter,
Yeah.
something that sifts through that digital flood for you.
Pretty much. It helps you get those crucial insights into the health, the security, the performance of your systems without getting buried in the raw data.
Okay, so our mission today is to really pull back the curtain on aiosyslogd.
Yeah, we want to explore what it is, how it uses some pretty neat Python techniques to get that speed, why its design choices make it so good for handling tons of logs.
And ultimately, what makes it such a powerful tool for anyone who has to deal with system logs, which is, let's face it, a lot of people.
It is. We'll look at how it handles data, the storage options, security stuff, and maybe even peek under the hood at some of the code that makes it tick.
Right, sounds great. So we've established logs are everywhere, and managing them is a massive headache. But let's just back up for a second. What is Syslog, fundamentally? Why is it so important here?
Okay, yeah, good question. So Syslog, at its core, is a standard protocol. Think of it like a common language.
A language for machines.
Yeah, exactly. It lets different devices, different applications on a network send their log messages to some kind of central collector.
So like my router talking to a server.
Precisely. It's how your router might report a dropped network packet, or your web server notes a successful user login, or maybe your operating system flags a critical event. It's been around for ages, evolved over time.
But it's still the standard way machines report what's happening.
Pretty much the universal way, yeah, for status updates, errors, activities, you name it.
Now, I remember the source mentioning it's not just one single format. There are different versions, like an older one and a newer one. Why is that? And what problem does aiosyslog solve by dealing with both?
Ah, right. That's a really practical point. So, historically, a lot of syslog traffic used what's called RFC 3164. It's older and honestly a bit looser in its structure.
Meaning it can be kind of messy to parse.
It can be ambiguous sometimes, yeah. The modern standard, though, is RFC 5424. This one's much more rigorous, more structured. Designed for precision, easier for machines to parse reliably.
Okay, so the headache is you've probably got both kinds floating around your network.
Exactly. That's the practical headache. You'll have older devices maybe still spitting out RFC 3164, while your newer apps are using the nice, clean RFC 5424. If your log collector can't handle both, you'd be trying to analyze logs in two different dialects.
Which sounds like a nightmare for trying to get a consistent picture.
A total nightmare for consistent analysis or any kind of automated processing.
So aiosyslog steps in here as a kind of universal translator.
That's a great way to think about it. It includes this really important utility that can take those older RFC 3164 messages and convert them on the fly into the modern structured RFC 5424 format.
So it normalizes everything.
Precisely. It means you can feed logs into it from all sorts of sources, old gear, new software, whatever, and aiosyslog smooths it all out into a single consistent schema before storing it.
That's huge for compatibility. And future-proofing, I guess.
Absolutely. It ensures compatibility across your whole setup, and it makes your log analysis way more reliable. Without that conversion, you're stuck with messy, inconsistent data. Good luck doing effective troubleshooting or accurate security analysis with that.
Makes total sense. Okay, so the project description uses terms like high performance and asynchronous. Let's unpack asynchronous.
Yeah.
For listeners maybe not deep into Python, what does that actually mean here? Why is it so important for handling, a ton of logs?
Right. So aiosyslogd leans heavily on Python's Asyncio library. Let's use an analogy. Imagine a really busy restaurant kitchen with just one chef.
Okay, one stressed chef.
Maybe. Now, a synchronous chef would take an order, cook that one dish completely from start to finish, wait for the water to boil, wait for the oven, wait for the sear, and only then start the next order. If they're waiting for the pot to boil, they're just standing there.
Wasting time.
Exactly. Now, an asynchronous chef takes an order, puts the water on to boil, and while it's heating up, they switch to chopping veggies for another order, or maybe plating a dessert for a third. They're constantly doing something useful, not just waiting idly for things like, well, I/O operations to finish.
I see. So it's like super efficient multitasking, but
Yeah.
with just one core worker, or one chef in this case.
That's it, exactly. In aiosyslogd, the chef is the server process, and the dishes are the incoming log messages. Instead of handling each log one by one, waiting for, say, the database write from message A to finish before even looking at message B,
It juggles them.
it juggles them. Asyncio lets the server handle thousands of these messages concurrently. It can kick off a database write for one log, and while that's happening in the background, it can immediately start parsing the next incoming message or queue up another one.
Okay, and that's the key to handling high volume without getting totally bogged down.
Absolutely key. It prevents bottlenecks, means the server isn't constantly waiting around, so it can keep up with that fire hose of logs without dropping messages.
Got it. Now there's also mention of loop or win-loop. The source says aiosyslogd supports of loop for a C-based event loop, making it one of the fastest ways to run Asyncio. Why is C faster here, and why does that matter for a Python program?
Ah, that's a great point. It touches on something called Python's Global Interpreter Lock, or the GIL.
The GIL, right, heard of it, limits true parallelism in standard Python.
Often, yeah. For CPU-bound work, it means only one thread might be executing Python bytecode at a time, even on a multi-core machine. But ovloop and winloop on Windows are different. They are highly optimized replacements for Asyncio's default event loop, written in C.
Okay, so they're outside the normal Python execution model in a way.
For I/O, yes. Because they're in C, they can handle network operations like waiting for a log message to arrive, or disk operations like write into the database much more efficiently. They can essentially release the GIL during these waiting periods.
Meaning Python isn't just sitting idle while waiting for the network.
Exactly. Ovloop handles that wait super efficiently in C, letting Python get ready for the next task immediately. This translates directly into significantly higher throughput.
So aiosyslogd with of loop can process way more messages per second than with the standard Python event loop.
Far more, especially for I/O-heavy workloads like a Syslog server.
Okay, so if Asyncio is the efficient multitasking chef,
Uh-huh.
then of loop is like giving that chef, I don't know, super fast knives, cutting boards made of pure speed, an oven that heats instantly. It just makes all those waiting parts, the I/O happen much, much faster.
That's a perfect analogy. It really is about optimizing those I/O waits. It shows aiosyslogd isn't just using modern Python features, it's using tools that push Python's performance for these kinds of tasks into territory usually dominated by lower-level languages.
Right. And, okay, connecting this back to the listener, why should you, listening now, care about Asyncio and of loop?
Well, because it's the technical underpinning of aiosyslogd's main promise, handling thousands of concurrent messages with minimal overhead.
Which means practically.
Practically, it means fewer dropped logs, more reliable monitoring for your important systems, a much more accurate, near real-time picture of what's actually happening inside your infrastructure.
It's the difference between catching a problem as it happens versus finding out hours later because your log server couldn't keep up.
Exactly that. Proactive insight versus reactive cleanup.
Okay, that makes a ton of sense. So we have this incredibly fast, asynchronous way to receive logs. But once you've caught all those digital breadcrumbs, what happens then? How does aiosyslogd actually store them and let you make sense of them?
Yeah, that's the next crucial piece, and this is where its flexible database backends come in. aiosyslogd gives you choices, primarily between two main options.
Choices tailored to different needs, I assume.
Precisely. Each has its strengths depending on your scale and requirements.
Let's start with the first one, SQLite. Now, I usually think of SQLite as, simple, embedded file-based, good for maybe small apps or desktops. How does aiosyslogd use it effectively for potentially huge volumes of logs?
It's a common perception, but the way aiosyslogd uses SQLite is actually quite clever and specifically designed for logs. Instead of creating one potentially massive, unwieldy database file,
Which would get huge fast.
right, it writes incoming messages to a SQLite database, but, and this is key, it creates a separate database file for each month.
Oh, interesting. So you'd have like syslog 22506.sqlite3 for June, then syslog 22507.sqlite3 for July, and so on.
Exactly like that.
That sounds really smart for managing data long term. What are the benefits of splitting it up like that?
It makes maintenance and backup way, way easier, which is a huge deal for anyone managing logs over time.
Yeah, I can imagine. Trying to back up a single multi-terabyte file that's constantly being written to sounds awful.
It's impractical, but with monthly files, they're smaller, much more manageable. Archiving old data becomes simple. You just move or compress the file for, say, last January. Deleting old logs is just deleting a file. It doesn't impact your current logging or the performance of queries on recent data.
And restoring data for a specific period, maybe for an audit.
Much simpler. You grab just the relevant monthly files, not one giant monolithic thing. It's a really pragmatic approach to the whole data lifecycle management problem.
Okay, that monthly partitioning is smart. Now, the source also mentions something called FTS5 for full-text search within these SQLite files. What is FTS5, and how does it make searching logs powerful?
FTS5 stands for Full Text Search version 5. It's a specialized module built right into SQLite itself.
Not an add-on, it's part of SQLite.
It's an extension, but commonly included, and it's designed specifically for doing really fast Google-style searches inside large amounts of text.
Okay.
So for each of those monthly SQLite files, aiosyslogd creates the main system events table to hold the structured log data, but then alongside it, it creates a corresponding system events FTS virtual table.
A virtual table.
Yeah, it's basically a specialized index powered by FTS5. It automatically indexes the content of the message field from your logs and potentially other text fields too.
So if I'm frantically searching for, say, a specific error code like database connection failed, or maybe tracing users' actions, looking for user admin logged out across maybe gigabytes of logs spread over several months, FTS5 makes that fast.
Instantaneous, pretty
Yeah.
much. Without FTS5, searching the message content in a big SQLite table would mean scanning every single row sequentially. Painfully slow.
Yeah, useless for urgent troubleshooting.
Totally. But FTS5 pre-builds an index, kind of like the index in the back of a book. It knows exactly where every word appears. So when you search, aiosyslogd's web UI can use this FTS index to find the matching log entries in milliseconds, even across huge amounts of data.
Wow. Okay, so it turns that potential haystack of logs into something genuinely searchable.
Exactly. It makes digging through historical data for troubleshooting or incident response incredibly efficient.
That's a massive usability boost.
Yeah.
But Squoodle is still embedded, file-based. What about the other option mentioned, Milosearch? Why would someone choose that instead?
Right, Milosearch is the other main backend option. aiosyslogd can optionally send the logs there instead of, or maybe even in addition to, SQLite. Milosearch is different. It's a fast, lightweight, but dedicated open source search engine.
Dedicated meaning it runs as a separate service.
Yes, it runs as its own process. While SQLite with FTS5 is fantastic for many use cases, especially simpler or single server setups, Milosearch is often chosen for, let's say, larger scale deployments, maybe distributed systems, or situations where search capabilities are absolutely paramount and you need more advanced features.
Okay, what kind of advanced features does Milosearch bring to the table that SQLite FTS5 might not have?
Well, it also does automatic monthly indexes, keeping things organized, but then it offers things like more sophisticated filtering options on specific log fields, complex sorting of search results, and a feature called proximity precision.
Proximity precision, what's that?
It means if you search for, say, database connection failed, Milosearch understands you probably want results where those words appear close together in the log message, not just anywhere in the message separated by paragraphs of other text. It ranks results based on how close the search terms are.
Oh, okay, that could be really useful for finding very specific events.
It can be, yeah. It helps pinpoint context. Milosearch is also designed with APIs in mind, so integrating its search capabilities into other tools or custom dashboards can sometimes be more straightforward than querying SQLite files directly.
So if I'm setting up aiosyslogd, how do I choose? What are the key trade-offs between SQLite and Milosearch?
It really boils down to a few things: scale, operational complexity, and your specific search needs.
Okay.
SQLite is embedded. It lives with aiosyslogd, uses local files. It's generally simpler to set up and manage, fewer moving parts. Great for single servers, small to medium log volumes, or if you prioritize simplicity.
Makes sense. And Milosearch.
Milosearch is a separate service. You have to install it, run it, manage it, so a bit more operational overhead. But it's built from the ground up as a dedicated search engine designed for high performance and scale. If you're dealing with truly massive log volumes, need those advanced search features like proximity, have a distributed setup, or want easy API integration for search, Milosearch is likely the more powerful and scalable option.
So it depends on whether simplicity or advanced search scale is the bigger priority.
Pretty much, yeah. It's about matching the tool to your specific environment and requirements.
But regardless of which backend you pick, that automatic monthly management of tables or indexes sounds like a lifesaver.
Oh, it's huge. Absolutely vital for long-term sanity. It prevents that classic problem of a single database table growing uncontrollably large and slow.
Yeah, I've seen that happen. Queries take forever.
Exactly. Logs are inherently time-based data, so partitioning them by month just makes sense. It simplifies cleanup, archiving, backups, and keeps query performance snappy for recent data. aiosyslog handles creating the new table or index each month automatically. You don't have to think about it.
Set it and forget it, mostly.
That's the idea. It keeps your storage manageable and your searches fast as data accumulates over time.
Let's zoom back in on that RFC 5424 conversion utility. The source mentions the file aiosyslogd drfc 5424.py and regular expressions. What's the core difficulty in parsing real-world logs? Why isn't it just straightforward?
The challenge is, even though Syslog is a standard, the actual implementations out there, especially for the older RFC 3164, can be, well, inconsistent.
Devices just don't follow the rules strictly.
Sometimes, yeah. The format is quite loose. You expect month, day, HHMMSS, host name, tag, PID, message, but maybe the timestamp format varies slightly. Maybe the PID isn't in brackets. Maybe the tag has weird characters. It's messy.
So aiosyslog needs to be flexible but also precise.
Exactly. It uses carefully crafted regular expressions, those patterns defined in RFC 5424.py, to match these common variations. It's built to be resilient to the kind of slightly off-spec logs you inevitably encounter in the real world.
Okay, so it uses regex to find the pieces. How does it actually extract them reliably?
The convert TFC 3164 to XE 5424 function is the heart of this. It tries to match the older format, then intelligently pulls out the priority level, the timestamp, the host name, and the raw tag part.
And that tag part can contain stuff like the app name and process ID, right?
Often, yeah. And it uses another pattern, PID pattern, to specifically look for and extract that process ID if it's embedded within the tag, like appname1234. It separates appname into the application field and 1234 into the PID field. This detailed normalization into the structured RFC 5424 format is absolutely essential.
Essential for getting clean, consistent data into the database for later analysis.
Couldn't analyze it effectively otherwise.
And the timestamp parsing. That sounds like it could get really tricky. Different time zones, clocks being slightly off, logs crossing over midnight or even New Year's. I heard there was a clever bit of logic for handling year boundaries.
Oh yeah, that's a classic log processing headache. And aiosyslogd has a really neat check for a subtle edge case. Imagine a log timestamped Daylo 31st, 11.59.59 p.m.
Right at the end of the year.
But maybe it doesn't actually get processed by the aiosyslog server until a few seconds later on January 1st of the next year.
Ah, okay. So when Python parses D32 on 11.59.59 on Jan 1st,
it might default to assuming the current year, January 1st year, making the log look like it's from the future.
which would mess up all sorts of time-based analysis.
Totally. So the code has this check. If dtnaive now, dtnaive.replace, year now.year1. If the parse timestamp, dtnaive, appears to be later than the current time now, it assumes it must be from the previous year and adjusts the year accordingly.
Wow, that's thinking ahead. It's a small detail, but it shows real attention to the messy realities of log processing.
It really does. It ensures your timestamps are accurate and your data is reliable, no matter when the log actually hit the server versus when it was generated.
So let's play devil's advocate. What happens if you don't have this kind of careful conversion and timestamp handling?
Right.
What's the real-world impact for someone trying to analyze system behavior or respond to a security breach?
The impact is pretty bad, honestly crippling. If your logs are inconsistent, malformed, or have incorrect timestamps.
Your database is full of junk data, basically.
Pretty much. Or at least data you can't fully trust or easily compare. This makes effective troubleshooting incredibly hard. You might miss critical events entirely, misunderstand the sequence of events because timestamps are wrong, or just waste hours trying to manually clean up or interpret messy entries.
And for security analysis.
Even worse, an analyst might completely fail to connect the dots between related suspicious activities because the logs look different or are out of order. They could miss indicators of compromise, struggle to build an accurate timeline of an attack, or just get bogged down in data cleanup instead of actual analysis.
So that conversion utility isn't just a nice to have. It's fundamental for reliable system monitoring and security.
Absolutely fundamental. It's about data integrity.
Okay, we've dug deep into the architecture and data handling. Let's switch to the practicalities. How does someone actually get aiosyslogd up and running? Is it complicated to deploy and configure?
One of the really nice things is its strong support for containers like Docker or Podman. The project provides pre-built container images.
Which makes it easier to get started.
Way easier. It's probably the most convenient way for many people, whether we're just trying it out locally or deploying it for real.
Why are containers so convenient here? What's the big win?
Well, containers bundle the application aiosyslogd in this case, along with all its dependencies, Python version, everything into one neat package.
So it runs the same everywhere.
Exactly. You get a consistent environment every time, no matter what operating system your host machine is running or what libraries you have installed locally. It gets rid of those classic, well, it works on my machine problems.
Yeah, hate those.
And it makes deployment and scaling much simpler. Need another log collector? Just spin up another identical container instance. It also really helps with CI/CD pipelines for development teams, ensuring consistency from dev to staging to production.
And the project keeps these images up to date.
Yep, it follows good practice, builds the latest image from the main development branch, and specific version tags whenever a new release comes out, shows it's actively maintained.
Okay, so if I want to just try it out quickly using Docker, what would that command look like? What are the key parts?
All right, let's break down a typical Docker run for the server. First, you'd probably docker pull key.iocw tiosyslog.latest to get the image.
Okay, got the image. Now run it.
Yep, something like docker run syst name iosyslogd-server -p 5140.5140 udp-v path to your data.dataquee.iocw tiosyslogd.latest.
Okay, let's unpack that. -D.
-d means detached mode. Runs it in the background so your terminal isn't stuck watching its logs.
Name aiosyslogd server.
Just gives the running container a friendly name, makes it easier to manage later, like docker stop aiosyslogd server.
DetGP 5140.514 UDP. Port mapping.
Exactly. That maps port 5140 using the UDP protocol on your host machine to port 5140 inside the container. That's how logs sent to your machine on that port actually reach the aiosyslogd process listening inside the container.
You'd probably need another DP for the web UI, maybe on a TCP port.
Right, usually something like narsp 5141.5141 TCP for the web UI. Using UDP for the high-volume, potentially lossy syslog traffic, and reliable TCP for the web interface connection.
Okay, now the ASV path to your data, that data part, that looks important. Volume mounting.
Absolutely critical. That's for persistence. Containers themselves are ephemeral. Their internal file system disappears when the container stops or is removed.
So without NaraV, all your logs would vanish on restart.
Poof.
Gone.
The ASV flag mounts a directory from your host machine, like path to your data, into the container at the specified path data. This means aiosyslogd writes its logs and config files to that mounted directory, which lives safely on your host file system, completely separate from the container's lifecycle.
So your data survives container restarts, updates, removals. Essential.
Non-negotiable for storing logs, yeah.
Now, it looked like the server and the web UI could run in separate containers. What does that tell us about the architecture?
It suggests a modular, kind of microservices-friendly design. While you can run both in one container, splitting them offers flexibility.
Like running the server closer to the log sources.
Yeah, maybe put the server on a beefier machine optimized for ingest, and the web UI on a different machine that's easier for users to access. It also lets you scale them independently.
So if log volume spikes, you scale up just the server containers.
Exactly. Or if lots of people are hitting the web UI, you scale that part up. More resilient, more flexible deployment options.
Okay, containers are great, but can I just install it directly, maybe for local testing or if I'm not using containers?
Absolutely. Standard Python installation works. Pip install aiosyslogd.
Simple enough, but what about getting that of loop speed boost we talked about?
For that, you install it with an extra. You'd run pip install aiosyslog speed. That pulls in of loop or win loop automatically.
So you can choose Simple install or max performance install?
Yep, caters to different needs. Quick test setup versus production optimization.
How about configuration? Once it's installed, is it a pain to set up?
Nope, it's designed to be pretty easy. It uses the TOML format for its config file.
TOML. That's the one that's quite human readable, right?
Yeah, much nicer than JSON or YAML for simple config, I think. By default, it looks for a file named aiosyslogd.toml in the directory where you run it.
And what if it doesn't find one? Does it crash?
Even better, on the very first run, if it doesn't find aiosyslog.toml, it actually creates a default -iosyslog.toml file for you with all the default settings.
Oh, that's nice. So it works out of the box and gives you a starting point to customize.
Exactly. Lowers the barrier to entry quite a bit.
What if I need to put the config file somewhere specific, like an etc., on a Linux server for a production setup?
Standard practice. You use an environment variable, aiosyslog.config. You set that variable to the full path of your custom config file, like export aiosyslog.tompic to config kaisyslog config.toml, and then run aiosyslogd.
Okay. And I read there's a difference in behavior here. If you specify a custom pass and the file isn't there.
Right. This is an important safety check. If you don't specify a path and the default isn't there, it creates the default. But if you do specify a path with aiosyslog to config and that file is missing, the server will not create a fault. It will exit with an error.
Why the stricter behavior for custom paths?
It's a safeguard for production. It prevents the server from accidentally starting up with potentially insecure or incorrect default settings when you explicitly intended it to use your carefully crafted production configuration. It forces you to be deliberate about your production setup.
Makes sense. Safety first in production. So what are some of the key knobs you can turn in that aiosyslogd.toml file? What can users actually configure?
There are several key sections. The server section lets you set the bin dip and bind port for listening to logs. Crucially, it also has debug and log dump flags, which are super helpful for troubleshooting.
See exactly what's coming in.
Yeah. Then the database section is where you choose your driver, SQUITE or Mailasearch. And very importantly, you set the batch size and batch time out for writing to the database. There's also a squal dump option there for seeing the generated SQL.
Batch size. That sounds performance critical.
Hugely. We'll come back to that. Finally, the web server section controls the web UI's bin dip, bind port, and has the redact option for hiding sensitive data in the UI.
So quite a bit of control to tailor it to your specific needs and environment.
Definitely. You can tune it for a small local test or a large-scale, high-security production deployment.
Okay, let's circle back to that database.batch size.
Mhm.
You said it was critical for performance. How does it work, and what's the impact of changing it?
So batch size determines how many log messages aiosyslogd collects in memory before writing them all to the database in a single transaction.
Instead of writing every single message individually.
Right. Writing messages one by one would be incredibly inefficient for the database, way too much overhead per message. Batching them significantly improves write performance.
So bigger batch size equals better performance. Just set it really high.
Not necessarily. There's a crucial trade-off. A larger batch size is more efficient for the database itself, fewer larger writes. But it means messages sit in memory longer before being persisted.
And if the server gets hit with a massive flood of logs while it's holding a large batch.
Exactly. The incoming network buffer in the operating system can fill up while aiosyslogd is busy processing or waiting to write that large batch. If the buffer overflows, the OS just starts dropping new incoming log packets.
Poof. Lost logs again.
Lost logs. So a larger batch size increases efficiency, but also increases the risk of dropping logs under heavy, sustained load if the database can't keep up with writing those large batches quickly enough.
Oh, so what about a smaller batch size then?
A smaller batch size means more frequent, but smaller, database writes. This is quicker per batch, so it reduces the risk of that network buffer overflowing. You're committing data to disk more often.
Less chance of dropping logs under load.
Right. But the downside is potentially higher I/O overhead on the database because you're doing many more individual write transactions. It might tax your disk more.
So it's a balancing act, dependent on your hardware, network, log volume.
Totally dependent. CPU speed, disk speed. Is it a fast SSD or a slow spinning disk? Network latency, the average rate and burstiness of your log traffic, it all plays a role. The default, I think it's 100, is usually a reasonable starting point.
But how do you find the optimal value for your specific system? It sounds like you need to experiment.
You absolutely do. And aiosyslogd provides a handy tool for this, a benchmarking script called login.py located in the scripts directory.
A log generator. How do you use it for tuning?
It's a practical iterative process. First, you'd edit your aiosyslogd.toml and set server.debug true so you get detailed output from the server.
Okay, start the server in debug mode.
Right. Then, in another terminal, you run python scripts login.py. You can tell it how many logs to send, maybe like 100,000 to simulate a heady burst.
Okay, blast the server with logs.
Yep.
Login.py will tell you how many it successfully sent. Then, the crucial part. You go look at the aiosyslogd server's debug logs.
And what are you looking for there?
Every time aiosyslogd successfully writes a batch to the database, it logs a message saying something like, wrote X messages to database. You need to add up all those X values from the server log during your test run.
Ah, so you compare the total number the server wrote to the number login.py sent.
Exactly. If the server wrote 100,000, or very close to it, then your current batch size is handling the load fine. Your system can keep up.
But if the server wrote significantly fewer, say 95,000.
That means your batch size is likely too high for your hardware. The server couldn't write the batches fast enough, the network buffer overflowed, and you dropped 5,000 logs.
Ouch. So then you'd lower the batch size in the config.
Lower the batch size, restart aiosyslogd, run login.py again, check the logs again. Repeat until you find the highest batch size your system can handle without dropping messages during that simulated burst. That's a really concrete way to optimize. It's not guesswork. It's data-driven tuning for your specific setup.
It really highlights that performance tuning, especially for high-volume stuff, isn't one-size-fits-all. You have to benchmark on your target hardware and workload.
Makes sense.
Yeah.
Now, what about fitting aiosyslogd into existing setups? Many places already use aiosyslogd, which is like the granddaddy of Syslog servers, right? Why would you use both together?
Good question. The main reason is often privilege separation. It's a really important security best practice.
Privilege separation, meaning running things with the lowest necessary permissions.
Exactly. The standard Syslog port is 514, both UDP and TCP. On Unix-like systems, ports below 2024 are privileged ports. Only the root user, or processes with special capabilities, can bind to and listen on those ports.
Ah, so Syslog, being mature and often part of the OS, is designed to run as root initially to grab that privileged port 514.
Right. It's battle-tested for securely handling that initial network reception. Now, you probably don't want your potentially newer, maybe Python-based aiosyslogd process running as root.
Yeah, that feels like a bigger attack surface if something goes wrong in aiosyslogd.
Precisely. So the secure pattern is let syslog run as root, listen on port 514, then configure syslogs to simply forward all the logs it receives over to aiosyslogd.
And aiosyslogd would be running as a normal, non-privileged user.
Yep. Running as a dedicated, unprivileged user like aiosyslogd or nobody. Listening on a non-privileged port, say 5140.
So aiosyslogd is the hardened front door on the privileged port, and aiosyslogd is the processor running safely as a regular user.
That's the pattern. It minimizes risk. If aiosyslogd were somehow compromised, the attacker wouldn't immediately have root access to the whole system.
Okay, that's a strong security argument. So if I already have syslogd collecting logs, how do I tell it to forward them to aiosyslogd?
It's usually pretty straightforward. The documentation for aiosyslogd likely has an example rsyslog config snippet, often called something like rsyslog-forward.conf.
What does that config typically look like?
The core part is usually a simple forwarding rule, like at 127.0.1.5140.
It means all logs.
Yep, all facilities, all priorities. The @ indicates UDP forwarding. You might use that @ for TCP to localhost 127.0.1 on port 5140 where aiosyslogd is listening.
Simple enough. But what if aiosyslogd is temporarily down, maybe restarting for an update? Does aiosyslogd just drop the logs then?
Ah, that's where aiosyslogd's robustness comes in. Good forwarding configurations include queuing mechanisms. You'll see settings like action queue file name, action queue max disk space, action queue save on shutdown, action queue type link list, and importantly, action resume or reach recount and naser1.
Whoa. Okay. What do those do?
They tell Syslog, if you can't immediately forward a message to aiosyslogd because it's down or slow, don't just drop it, instead queue it up. The queue can be in memr, linked list, and or spooled to disk, action queue file name. Action queue max disk space limits how much disk it uses, and action queue save on shutdown makes sure the queue is saved if aiosyslogd itself restarts. Action resume read count nice1 tells it to keep trying to send the queued messages forever until aiosyslogd comes back online.
Wow. So syslog acts as a reliable buffer, preventing log loss even if aiosyslogd has a hiccup.
Exactly. It adds a layer of resilience to the whole pipeline, critical for ensuring you don't lose data during maintenance or unexpected outages.
What about setting up aiosyslogd purely as a dedicated forwarder, like on a machine that doesn't need to log its own stuff, just receive and forward.
Yeah, you can do that too. There's often a rcslog-minimal.conf example. The idea there is to strip rsyslog down to the bare essentials.
Oh, so?
It unloads modules it doesn't need for forwarding, like imclog, kernel logging,
Hmm.
or imuxsock, local sockets logging. It configures just the necessary input module, like imup for UDP on port 514, and the output module, omstowd, to send everything straight to aiosyslog.
So it becomes a lean, mean forwarding machine focused just on that one job securely.
Precisely. Minimal resource usage, minimal attack surface, a clean, efficient way to implement that privilege separation.
Cool. Now, one last deployment angle mentioned.
Mhm.
Using aiosyslog not as a server, but as a library within another Python application. What's the use case for that?
This opens up some interesting possibilities for developers building custom tools. The core logic for receiving and parsing syslog messages, the syslog UDP server class, can be imported and used directly within your own Asyncio-based Python application.
So instead of running aiosyslog as a separate process, I could embed its listening capability into my own app.
Exactly. Imagine you're building, say, a custom real-time network monitoring dashboard that needs to directly ingest syslog from routers or firewalls. Or maybe a specialized security information and event management SIME tool that performs complex correlation and needs raw syslog feeds as one of its inputs.
So you wouldn't have to reinvent the wheel of handling syslog protocols and parsing.
Right. You can leverage aiosyslog's optimized asynchronous UDP server and its robust RFC 5424 conversion logic as a component within your larger application. It saves a ton of development effort and lets you benefit from its performance characteristics directly.
That makes it more of a building block, not just a standalone tool.
Yeah, it expands its utility quite significantly for custom development scenarios.
Okay, that covers deployment and integration pretty thoroughly. Let's shift focus slightly to the user experience, security details, and maybe the overall philosophy driving this project. First up, the Web UI aiosyslogd web. What's its main goal?
Its main role is to provide a simple, straightforward way to actually see and search the logs that aiosyslog has collected. It runs as a separate component, usually, and you access it through your web browser.
And it's built using Quart. Is that like Flask or Django?
It's similar to Flask, but crucially, Quart is an asynchronous web framework. It's built on top of Asyncio, just like aiosyslogd itself.
Ah, so the web UI is also non-blocking and can handle multiple users searching logs concurrently without grinding to a halt.
That's the idea, yeah. Keeps the whole stack asynchronous and responsive from log ingest right through to the user interface.
Smart. So what can you actually do in this web UI? What features does it offer for digging through logs?
Looking at the template code gives a good idea. It dynamically lists the available monthly 65 Lite databases, available to Brubs, so you can easily pick which month's logs you want to look at.
Easy historical navigation. Nice.
Yep. Then there's a main search bar, search query, for your basic keyword searches, leveraging that FTS5 index we talked about.
Fast searching.
Right. And it also has more advanced filters. You can filter by the sending host name from host, or specify a precise time range using received@min and received@max.
So you can really zero in on logs from a specific machine during a specific incident window.
Exactly. It also handles pagination automatically, showing logs in manageable chunks rather than trying to load like a million logs into your browser at once.
Yeah, that would crash my browser for sure.
Definitely. And for developers or admins debugging performance, there's even an option to show executed SQL.
Oh, wow. So you can see the exact SQL query the UI sent to Swy.
Yep. Incredibly useful for understanding why a particular search might be slow or for optimizing your queries. It also has a dynamic highlighter for your search terms within the log messages, making it easier to spot the relevant bits.
That sounds pretty functional. I also saw a note about it defaulting to showing only the last hour of logs when you first load it without filters. Why do that?
That's a really thoughtful usability feature. Imagine you have years of logs stored. If the UI tried to load everything by default when you first opened it.
It would take ages and probably time out or crush the server.
Exactly. By defaulting to just the last hour, it gives you an immediate view of the most recent activity, which is often what you want for quick monitoring without overwhelming either the server or your browser. It makes the initial experience much faster and more responsive. You can then broaden the time range or apply filters if you need to look further back.
Simple but effective design choice. Now there was an important caveat mentioned. This web UI is specifically for the SQLite backend only.
Yes, that's a crucial point. The code explicitly checks for this. If you configure aiosyslogd to use milesearch as its database driver.
This aiosyslog web component won't work with it.
Correct. You wouldn't use this built-in UI. milesearch is its own separate search engine. You'd interact with it using its own API, or potentially use one of the several general-purpose web UIs designed specifically for milesearch to explore your log data stored there.
Okay, good to know. Avoids confusion if someone picks milesearch. Now let's talk sensitivity. Logs often contain stuff you might not want everyone seeing: usernames, IP addresses, maybe internal host names. How does aiosyslogd handle privacy and compliance concerns? The redaction feature sounded interesting.
Yeah, this is super important, especially with regulations like GDPR, IPA, etc. Logs are incredibly valuable, but they can easily contain personally identifiable information, PII, or sensitive operational details.
Usernames, IP addresses, MEL addresses.
All that stuff. The redact option in the aiosyslogd.toml file, specifically for the web server section, controls this. When enabled, it activates a redact function that processes log messages before they are displayed in the web UI.
Before display, so the original data in the database is untouched.
Correct. It's redaction at the display layer, not modification of the source data. This is usually preferable, as you might need the original data for deep forensic analysis later, but you don't want it casually exposed in the day-to-day UI.
Okay, how does it know what to redact?
It uses a set of predefined regular expressions, things like user pattern, IPv4 pattern, IPv6 pattern, MAC pattern. These are designed to match common formats for usernames, different types of IP addresses, including loopback and MMAC addresses.
And when it finds a match.
It replaces the match text with a redaction character. Usually it's that solid block character but there might be an option for a different one like
So user Alice logged in from 10 Tiope 0.5 becomes user Yoker logged in from in the UI.
Something like that, yeah. It effectively masks the sensitive parts while still showing the structure of the log message.
That's a really valuable feature for security and compliance, letting people view logs without accidentally leaking private data. Beyond redaction, what about the project's overall security posture? Is there a formal policy?
Yes, there's a security.md file which outlines the policy. It's quite responsible, especially for an open source project. It clearly states which versions get security patches, typically the latest release and the current development branch head.
So older versions are explicitly not supported for security fixes.
Correct. Users need to be aware they should stay reasonably up to date to receive security patches. Standard practice for many projects.
How do you report a vulnerability if you find one? Do you just open a public issue on GitHub?
No, and this is important. The policy strongly requests private disclosure. You're supposed to email the maintainer directly using the address found in the license file
Why private?
to prevent zero-day exploits. Reporting it publicly before a fix is available gives attackers a heads up. Private disclosure allows the maintainer time to investigate, develop a patch, and coordinate a release before the vulnerability details become public knowledge.
Responsible disclosure. Makes sense. Does the policy say anything about timelines or acknowledgement?
It mentions an aim to acknowledge reports within 7 days, which is pretty good. And it follows a coordinated disclosure process. They'll work on a fix and then announce it publicly, usually giving credit to the reporter once the fix is ready.
That sounds like a solid, responsible approach to security handling. Now, something else that stood out was the Code Conducts TTMD. It seems a bit unusual, maybe, for a project primarily driven by one person to have such a formal co-C. What does that signal?
I think it signals a strong commitment from the maintainer, not just to the technical quality of the project, but also to fostering a positive, welcoming, and respectful environment for anyone who interacts with it, whether they're reporting bugs, suggesting features, or just asking questions.
What are the main points of the Code of Conduct?
The core tenets are pretty straightforward. Be kind, be respectful, give feedback constructively, own up to mistakes, and generally focus on improving the project collaboratively.
And things to avoid.
It explicitly calls out things like rude comments, trolling, personal attacks, harassment, basically. Don't be a jerk.
How does it suggest handling disagreements?
It encourages reaching out privately first to resolve issues respectfully. It outlines steps like asking for a pause if things get heated, and reserves stopping contributions as a last resort for persistent problems.
So, for someone listening, thinking about maybe contributing to aiosyslogd or a similar project, this sets clear expectations for interaction.
Exactly. It shows the project values not just code, but also community health and respectful collaboration. It means you know what kind of environment you're stepping into.
And briefly, the pyproject.toml file. What does that tell us?
That's the standard configuration file for modern Python projects using tools like Poetry, which this project uses, for managing dependencies and packaging. It formally lists the project name, version, description, author, the license, MIT license, which is very permissive open source, and the compatible Python versions, 3.11, 4.0. It's like the project's birth certificate and build instructions rolled into one, shows it's using modern Python packaging practices.
Okay, fantastic overview of the user-facing aspects, security, and philosophy. Now, for those listeners who really like to understand how things work under the hood, let's dive into some of the core code components. Where does the main server logic live?
The absolute heart of the server is in aiosyslogd server.py, specifically within the Syslog UDP server class. This class inherits from a Asyncio datagram protocol and handles all the low-level stuff of receiving UDP packets off the network.
UDP being the typical way syslog messages are sent. How does it cope with potentially thousands of those packets arriving per second without getting overwhelmed right at the network layer?
The key is decoupling receiving from processing using an internal queue. There's a message queue, which is an Asyncio queue.
Okay, good cue.
When the datagram receive method gets a UDP packet, it does the bare minimum, maybe decodes it, and then immediately puts the raw message data onto this message queue. It doesn't try to parse it fully or write it to the database right then and there.
So receiving is super fast, just grabbing the data and sticking it on a queue.
Exactly. Quick ingest. This prevents the network receiving part from becoming a bottleneck, even under heavy load. It acts as a buffer, smoothing out bursts.
Smart. So the messages pile up in the queue. What takes them off the queue and processes them?
There's a separate, dedicated asynchronous task called database writer. This task runs concurrently, and its sole job is to pull messages off the message queue and write them to the configured database backend.
And it does this in batches, right? Using that batch size and batch timeout we discussed.
Precisely. The database writer tries to pull batch size messages from the queue. It uses a syncio.waitFor with the batch timeout. This means it will wait up to batch timeout seconds to fill a batch. If the batch fills up sooner, great, it proceeds. If the timeout hits before the batch is full, it just processes whatever messages it managed to gather in that time.
So it ensures logs get written reasonably quickly, even if the traffic is low or sporadic, but still benefits from batching when the traffic is high.
Exactly. It balances efficiency with timeliness.
And where in this pipeline does the actual parsing and normalization to RFC 54224 happen?
That happens within the process datagram method, which is called by the database writer after it pulls messages from the queue. Once it has the raw message string, before sending it to the database driver, process datagram calls the conversion logic, if needed, and structures the data into that consistent RFC 5424 message object. That's the transformation point from raw string to structured data.
Okay. What about security within this core server code? Dynamically loading database drivers sounds like it could be risky if not done carefully.
Absolutely, and there's a specific safeguard for that. In server.py, you'll find a hard-coded Python set, allow the DB drivers a SLIght
With
mylist.
whitelist of permitted drivers.
Exactly. When the server starts up and reads the driver setting from your config file, it checks if the configure driver name is actually in this allowed set, using if DB driver, not in allowed drivers.
And if it's not, like if someone put my squall or something malicious in the config.
It immediately raises an error and exits. It refuses to even try loading an unknown or disallowed driver. This is a crucial security measure to prevent potential code injection vulnerabilities that could arise from loading arbitrary Python modules based on configuration input.
So it only loads code it explicitly trusts. Good. How does the server manage talking to potentially different databases like SQLite and Mailasearch without getting tangled in specific implementation details?
Through abstraction, it uses a technique common in good software design, an abstract base class, ABC. There's a base database class defined in aiosyslogd.py.
An ABC, like a template or a contract.
Exactly like a contract. The base database ABC defines a set of methods that any concrete database driver must implement. These include methods like connect, close, and the crucial write batch.
So the Syslog driver implements these methods one way, and the Mailasearch driver implements them in its own way.
Precisely. But the main Syslog UDP server code doesn't need to know how they implement them. It just knows it can call dbdriver.writeBatch messages and trusts that the driver, whichever one it is, knows how to handle writing those messages according to the contract defined by base database.
That makes the system modular. You could potentially add a new database backend later just by creating a new driver class that fulfills the base database contract.
Exactly. It promotes pluggability and makes the core server code much cleaner and easier to maintain, as it doesn't have database-specific logic scattered throughout it.
Nice engineering. Okay, let's zoom into the Sqularted driver in aiosyslogd squite.pia. How does it handle those monthly database files at the code level, making sure it switches smoothly?
There are helper methods for this. GetDB path for month figures out the correct file name, like sysloggyyymm.squite3 based on a log message's timestamp. Then, the switch if needed method checks if the current database connection is for the correct month for the incoming batch of logs.
And if it's not, like the first log of July arrives.
It detects the month change, gracefully closes the connection to the June database file, opens a new connection to the July file, creating it if it doesn't exist, and importantly, runs the necessary create table and create virtual table, using face statements to ensure the new month's database is properly initialized, all automatic.
Seamless transition. What about making Squilite perform well enough for potentially high write volumes? Any specific Squilite tricks being used?
Yeah, a couple of key Squilite pragmas and features are used. First, on establishing a connection, it executes pragma journal mode wall.
Whoa. Write-ahead logging, what does that do?
It's a different journaling mode for Squilite that significantly improves concurrency, especially write concurrency. In wall mode, writers don't block readers, and multiple readers can operate while a write is happening. This reduces contention and generally leads to better throughput under load compared to the default rollback journal mode.
Okay, better concurrency. What else?
The use of FTS5 itself is an optimization, but specifically, the way it's kept up to date using SQL triggers is very efficient. There are create trigger statements defined, like aiosyslogd deft insert, that automatically fire whenever a row is inserted, updated, or deleted in the main system events table.
So the triggers automatically update the system events FTS index table.
Yep. The FTS index is kept perfectly synchronized with the main data table by the database itself, automatically and efficiently. No need for aiosyslogd to run separate indexing processes or worry about the index getting stale. It makes the FTS reliable and always ready for fast searches.
Clever. Now, I heard the write batch method in the Squilite driver has optimizations called fast path and slow path. What's that about?
Ah, yes. This is a neat performance optimization within the batch writing logic itself. The driver first checks a simple condition. Do all the log messages in the current batch belong to the same month?
Which would be the case most of the time, right?
Vast majority of the time. If yes, that's the fast path. It can write the entire batch to the single correct monthly database file in one go using Squilite's efficient execute mini command for bolt inserts. Very quick.
Okay, so when does the slow path happen?
The slow path handles the rare but possible edge case where a single batch of logs actually spans a month boundary. For instance, a batch might contain the last few messages from 11:59 p.m. on June 30th and the first few messages from 12:00 a.m. on July 1st.
Ah, okay. So you can't write that whole batch to just one file.
Right. In the slow path scenario, the code iterates through the batch, partitions the messages into sub-batches based on their month, batches by month, and then calls a helper method, write sub-batch, to write each sub-batch to its correct respective monthly database file.
So it's slightly more work partitioning and multiple smaller writes, but it ensures the data still ends up in the right place, even across month boundaries.
Exactly. It's robust handling for that edge case. It prioritizes correctness, even if it's slightly less efficient than the fast path. Think of it like sorting mail. Fast path is a bundle all going to one house. Slow path is an envelope with letters for two different houses needing a quick resort.
Great analogy. That level of detail really builds confidence in its reliability. Okay, let's switch gears to the Search driver in aiosyslogd milesearch.py. How does it manage setting up indexes correctly in Search? And how does it handle writing batches asynchronously to what is essentially an external web service?
For setting up indexes, the ensure monthly index method is key. Since multiple aiosyslogd tasks might try to write logs concurrently, potentially needing to create or configure the same Search index for the first time in a month simultaneously.
You could have a race condition.
Exactly. So it uses an asyncio dot. Only one task can hold the lock at a time, ensuring that the check for index existence, index creation, client.createIndex, and applying index settings, index.update settings, happens atomically without multiple tasks interfering with each other.
Safe index creation. What about those settings?
The code programmatically defines the Search index settings, specifying which log fields should be searchable, which should be filterable or sortable, and enabling things like proximity precision for better search relevance. It configures the index optimally for log searching.
And Search needs unique IDs for every document, right? How are those generated?
Yes, each log message needs a unique ID when sent to Search. aiosyslogd generates this by combining the log's high-precision timestamp, converted to a string, removing the decimal, and its index position within the current batch, something like f timestamp string dash batch index. This guarantees uniqueness even if multiple logs somehow arrive with the exact same timestamp down to the microsecond.
Okay. Now the async writing part. Sending data over the network to an external service like milesearch can be slow. How does it do that efficiently without blocking Python's event loop?
The write batch method here is clever. It first groups the messages in the batch by the target monthly milesearch index. Then, for each index, it calls milesearch's adocuments method to send off the logs for that month.
But a documents just starts the indexing task on the milesearch server, right? It doesn't
Exactly.
wait for it to finish.
Correct. A documents returns quickly with a task UID for the background task milesearch has started.
Yeah.
Waiting for each of these tasks individually would be inefficient and potentially blocking.
So how does it wait efficiently?
It collects all the task UIDs returned from all the documents calls for the current batch. Then it uses asynchrony.gather along with the milesearch client's wait for task method for each UID. Asynchrony.gather runs all these wait for task calls concurrently, efficiently waiting for all the milesearch background tasks for that batch to complete without blocking the main event loop while waiting on network responses.
Leveraging Asyncio to wait for multiple external operations simultaneously. Very efficient.
Exactly. Key for performance when dealing with external services.
Okay, one last code dive. The sexlay utilities, specifically for the web UI. In aiosyslogd ddb's collectutils.py, there seem to be some smart tricks there to keep the UI fast, like get time boundaries and use approximate count. Can you explain those?
Right. These show optimization efforts focus purely on the retrieval and display side. For example, getAvailableDatabases needs to scan the file system to find all of the syslog.sclite3 files. File system operations can sometimes be slow and blocking.
Blocking the Asyncio event loop, which would make the web UI unresponsive.
Potentially, yeah. So it cleverly wraps the glob.glob call, which finds the files, inside asynchrony.thread. This runs the potentially blocking file system scan in a separate thread, preventing it from stalling the main Asyncio loop that handles web requests. Keeps the UI snappy.
Smart use of threads for blocking I/O. What about get time boundaries? That sounded like a query speedup.
It is a fascinating optimization specifically for time range queries in the UI. Imagine searching logs over the last 24 hours in a database with millions of entries per month. A simple where received at between start time and end time might require Scrilight to scan a huge portion of the table or index.
Which could be slow.
Very slow. So get time boundaries uses a heuristic, a kind of chunking search. It makes smaller, faster queries to find the approximate row IDs, started and ended, that correspond to the start and end times of your requested range. It might check IDs around estimated positions based on time increments, like 5 minutes, 15 minutes, 60 minutes ago.
So it quickly narrows down the range of row IDs it needs to actually query in detail.
Exactly. It avoids scanning potentially millions of irrelevant rows just to find the start and end points of the time window. Greatly speeds up fetching the first page of results for a given time range.
Then use approximate count. That sounds like it sacrifices accuracy for speed.
It's an optional trade-off, yeah. Calculating the exact total number of logs matching a query, select count, can be surprisingly slow on very large SQLite tables, especially with complex where clauses.
Sometimes slower than fetching the first page of results.
Often, yes. So, for certain queries, like simple unfiltered time ranges, where it has already found the started and ended, the UI can optionally estimate the total count by just calculating ended started plus 1.
Which is lightning fast, but not perfectly accurate if IDs aren't perfectly sequential or some were deleted.
Right. But for displaying something like showing 150 of approx, 500,000 logs in the UI, that approximation is often perfectly acceptable and vastly preferable to making the user wait potentially seconds or minutes just for an exact count before seeing any results.
So it prioritizes perceived performance and responsiveness in the UI.
Exactly. It's about balancing perfect precision with a smooth user experience, especially when dealing with potentially massive data sets.
Wow. Okay, the aha moment here really is seeing the depth of thought that goes into optimizing both ends of the process: super fast, reliable ingest, and fast responsive retrieval and display. It's not just about collecting data, it's about making it usable.
Precisely. It demonstrates a holistic approach to the log management problem, tackling performance bottlenecks all the way through the system.
And that brings us, I think, towards the end of this deep dive. We've really covered a lot of ground with aiosyslogd. We went from its core asynchronous design, the speed boosts from Loop.
Right, through the flexible database options like SQLite with FTS5 for powerful search and the scalable MilaSearch alternative.
We looked at the practicalities of deployment, using containers, configuration, performance tuning with login.py, and secure integration with Syslog.
And we explored the user experience side with the web UI, the crucial sensitive data redaction feature, the project's security policy, and even its code of conduct.
Plus, that peek under the hood at the clever code handling queues, database abstraction, wall mode, FTS triggers, batching optimizations, and those UI speedups. It's clear a ton of smart engineering went into this.
It really showcases how modern Python, combined with careful architecture and leveraging tools like loop and specific database features, can create seriously high-performance solutions for traditionally challenging problems like high-volume log management.
So, thinking bigger picture, what are the broader implications here? Why does a project like aiosyslogd matter in the grand scheme of things?
Well, think about how much of our world runs on software and network systems now. From massive cloud platforms down to tiny IoT devices, they all generate data, logs, telling us what they're doing.
And understanding that data is crucial.
Absolutely. The ability to efficiently collect, store, and analyze this machine generated information isn't just a niche technical task anymore. It's fundamental. It underpins cybersecurity, finding threats in the noise. It's vital for operational troubleshooting, figuring out why something broke. It feeds into business intelligence, understanding user behavior. It's necessary for compliance and auditing.
So, tools that make this process easier, faster, more reliable, they're enabling all those other critical functions.
Exactly. aiosyslogd represents a really powerful, accessible, and open source approach to solving a core piece of that puzzle. It helps turn that raw data deluge into actual usable insight for potentially anyone running systems.
Okay, so looking forward, we're generating more data than ever. Logs are getting even more voluminous. Where does log management go next? Is it just about faster storage and search?
That's a great question to ponder. Faster storage and search are always needed, but maybe the next real frontier is moving beyond just reactive analysis.
Toward something more proactive.
Maybe. Imagine real-time, AI-driven anomaly detection happening within the logging infrastructure itself. Not just storing logs, but actively analyzing streams as they arrive, identifying deviations from normal patterns, maybe even predicting potential failures or security issues before they have a major impact.
So the log system becomes less of a passive recorder and more of an active intelligence engine.
Potentially, yeah. Transforming those raw digital heartbeats directly into immediate actionable intelligence. What new kinds of insights, what level of system understanding could we unlock if we could instantly comprehend, correlate, and maybe even anticipate based on every single log message?
That's definitely something to think about. A future where logs aren't just history, but real-time predictive insight.
It's an exciting possibility. The data is there. The challenge is unlocking its full potential efficiently.
Well, on that forward-looking note, thank you for joining us on this deep dive into aiosyslogd. We hope exploring its architecture, features, and philosophy has given you, our listener, a valuable shortcut to being well-informed about this powerful tool and the challenges it tackles.